Okay, so the problem we are addressing is how can we represent and use general tactical knowledge? How do we get that out of there? I'm sorry. How can we use general tactical knowledge to improve performance and learning in a broad, complex domain like FreeCiv? Now, you may or may not be familiar with FreeCiv. It's an open source strategy game in which players try to build civilizations and try to conquer each other's civilizations. And it goes through phases. Instead of turn taking, you have phases where players can take multiple actions within a phase, and things can happen within a turn. So when we talk about tactics, we're asked, the kind of questions we're asking is should this catapult pursue a mobile adversary? Or down in Detroit here, there's a defender in Detroit, you can tell by the little fenestrations. Should the defender attack the chariot first, or should it wait and be passive? Okay, so let's define tactics a little more concretely. For us, a tactic is a composite goal-directed behavior that is sensitive to, I'm really having trouble with this talking thing. How do I get it out of here? Anyway, I'm sorry. How do I go back? Here we go. It's sensitive to adversarial actions and other external events. And in our model, tactics are not limited to military tactics, but can include economic investments, legal tactics, social and political tactics. And we want tactics to essentially to provide large building blocks for learning, rather than fine-grained actions, and to eventually learn to make better decisions about selecting and applying tactics, as opposed to inventing tactics from whole cloth. So we want to find a representation to support that, and then we want to actually use that in the game. So our desiderata for a representation is that it should be penetrable. We want to be able to reason about requirements, resources, and dependencies. That should be expressive, capable of representing complex scheduling and temporal constraints. It should be transferable. It shouldn't be specific to this particular game. And it should be learnable. So we should be able to decompose to individually learnable decisions. Okay, so the overall gist of this is that we treat tactics as neo-Davidsonian events. That means they're like frames and slots as opposed to positional notation of HTN tasks. And they have named roles and internal structure, and this allows us to represent partial information so that we can incrementally instantiate a tactic as resources and information become available. So here's an example. Here's a cartoon example of search and destroy. It's basically a finite state machine. It's got sub-events in it. It's got target picking, where you decide who you're going to go after, closing with the enemy, and you have to wait until you're in range, destroying the enemy force, and that may actually fail, or it may succeed, in which case you go back and pick another target. Okay, so that's fairly simple, and that's the idea. That's the extent of domain knowledge. To put that into formal statements that we can work with, this may look intimidating, but it's actually quite simple. It really follows that structure very, very closely. There are only 4 kinds of knowledge being expressed here. The first few statements are connecting the tactic to the rest of the ontology. So we're saying that search and destroy, for instance, is a military tactic. It's offensive. It's an iterative event type. It takes place over a large amount of time. It has roles. It has named roles. And so we have a doer, someone who actually performs the tactic. It has a location in this case. And it has sub-events. So we saw the sub-events before. They're target picking and waiting and closing with the enemy and destroying the enemy force. And then there are arbitrary temporal constraints. It's sort of a simple temporal network where you can express relationships and triggering between the different subevents. Okay, so that's all well and good, but we have to be able to actually use that. We have to be able to use that in the context of a real game. And so that's what we call operationalizing a tactic. So our definition for that is we're instantiating and translating an event type into plannable, executable actions supported by the architecture. And so given a small library of game-independent tactics, our tactical planner selects appropriate tactic types, has to bind participants to available game entities, translate them to game-specific HTN tasks, or maybe HGN, I don't know, and primitives, and schedule execution such that triggering conditions and sequencing constraints are honored. Actually, it is an HTN, I should be clear about that. So this is a way of achieving some of the more flexibility in the other types of planning. This happens in the context of our companion cognitive architecture, and that contains an agenda that supports priority queue of tasks, looping behavior, interleaved execution, and tactic instantiation and error handling tasks. All right, so more concretely, the way it works is because the goals, available entities, and primitive actions of the game are expressed in the vocabulary of the game, whereas the tactics are expressed in a domain-independent vocabulary, the tactical planner must dynamically map between them in order to make use of them. So it constructs and caches a discrimination tree to match game goal types to tactic types. It does that up front, and then it reuses it. It climbs the ISA hierarchy to match game entities to tactic participant roles. So we can't just unify, we have to actually climb up the ISA hierarchy. It maps the leaf event types to game action primitives or HTN tasks in the domain. And it translates scheduling constraints into companion native precedent relations on an agent's agenda. So this is a very short talk, so I can't go into much detail here, but basically, does it work? And we've implemented 3 initial tactic types: search and destroy, defending a position, and building out road networks. And the FreeCiv player now is able to build out road networks across its civilization, pursue mobile adversaries, and learns when and when not to attack approaching invaders, among other things. So with respect to the criteria we laid out earlier, and I'm sorry these are not metric, but they're qualitative criteria, we would say that this is a penetrable representation because there's an audit trail, an accessible audit trail from actions to tactics to goals. So the behavior is explainable rather than going all the way from primitive actions up to goals. It's expressive because the representation supports looping, waiting, failure handling, and structured behavior. It directly supports contingency planning, which is hard to do in a pure planning system because you have to be able to respond to external events. It's transferable in that the tactics are not specific to a game, though the game entities and actions must inherit from the general ontology. And it's learnable. By clearly distinguishing decisions from the intrinsic structure of a tactic, it's possible to learn to improve performance on that tactic. Now, this is not a learning talk, but we have done pilot studies. And in this case, this was an example of defending a position. Within the context of the tactic of defending a position, we wanted to learn when to attack and when to just stay still and be passive and not to attack. And what this shows is over 10 games, the percentage of successful attack. So the baseline is always attack. When an enemy comes within range, you automatically attack, and that doesn't do so well. What it does is it learns essentially when not to. It's using analogy to generalize the conditions under which it succeeded and when it failed, and we improved by 19% over 10 games. So just proof of concept. And so our conclusions are that ultimately background tactical knowledge can aid learning by providing 10-league boots, as it were, for exploration, and by clearly delineating learnable decisions and parameters. The purpose and structure of a tactic should not be specific to a concrete domain like FreeCiv, but criteria for selecting tactics and binding participants are things that should be learnable, are decisions that we ought to be able to learn independently. And that's a simpler problem than learning the whole structure of a tactic. And the mechanisms for operationalizing a tactic for a particular simulation, a game simulation in this case, and execution architecture are not conceptually difficult, but they're critically important for realizing performance benefits. And so that took the bulk of our time in developing this. And that's pretty much what I've got.